Thank you, Kelvin. Um, so welcome everybody to the power noise reliability sign-off uh, using RedHawk and Totem. I'm essentially going to be talking about advanced 28 nanometer low power design using the GlobalFoundries PDK kit. But before we go into that, I just wanted to give a quick introduction about Apache and ANSYS. Apache is a business unit in ANSYS. ANSYS has been a leader in multi-physics simulations that cover electromagnetics, thermal, mechanical, and multiple types of simulations in electronics. And Apache is a leader in power, noise, and reliability simulations at the IC level, covering all the way from IC to package to chip level analysis. Our unified simulation environment is going to provide a chip-aware system and a system-aware chip-level simulations with world-class support and simulation capabilities. Overall, we support an end-to-end chip package system-level power, thermal, electromagnetic interference, and a timing platform that covers different aspects of the chip package and the system. Let me talk about some of the issues that the industry has been seeing in the last few years. Um, the key issue that has always been plaguing us is the difference in the power requirement and the power budget that has been in today's low-powered electronics. We're increasingly seeing that integration of multiple types of components on the same die is causing the power budget to actually go higher and higher, but our battery limits can only sustain a certain percentage of power. So there is this growing difference between the limit that the battery can sustain and the power it can consume. We're also seeing that ensuring power delivery integrity, basically where your voltage supplies have been steadily decreasing and the threshold voltage of the different process nodes have not really changed. So we are seeing a decrease in the overall noise margins. So we're basically seeing two different areas. One is how to manage the power budget gap and how to ensure that the power delivery is accurate at your system and your die level. The other concern that has been plaguing us is how to mitigate IC reliability concerns. Reliability concerns typically contain electromigration or ESD. Electromigration is a time-based failure, whereas ESD is an event-based failure. And we are seeing decreasing electromigration limits for different process nodes, and we're also seeing a decrease in the ESD design window from one process node to another. Apache's comprehensive power, noise, and reliability platforms are basically solving the problems that designers are faced with the power delivery integrity, with the power budget gap, as well as the reliability concerns. Power Artist is Apache's power analysis and power reduction platform at the RTL level or at the architectural level. Totem is Apache's platform for IP level power noise reliability. And RedHawk is the SoC power noise reliability platform for full chip analysis with package impact as well as system impact. And finally, Sentinel is Apache's package level analysis platform for doing thermal, power integrity, signal integrity, and electromagnetic interference at the system level. We are not only proposing different tools for addressing different problems, but Apache also proposes different methodologies to solve different problems. In terms of methodologies for addressing low power design concerns, an RTL to gate methodology where the RTL level analysis is being performed for power reduction and feeding it to the physical world where a physical design is analyzed for reliability as well as voltage drop, and also for advanced reliability conditions like electromigration, ESD analysis, and thermal analysis need to be performed at the die level. And finally, a chip package system convergence is needed, where the impact of the die is felt at the system for doing system level design, and the impact of the system, basically through the package and board models, is felt on the die. So we will go into some of the details in terms of how Apache is addressing some of the 28 nanometer constraints, especially for the 28 nanometer process in GlobalFoundries. So typically, there are two types of reliabilities that we have been tracking. One is the power and ground noise reliability. So this leads to event-based failures over time, where if the proper event is not modeled during an IR drop failure, we're going to lead to system-level failures. And the other is chip reliability, where power and signal line electromigration is a major component of time-based failure, and ESD is a major component of event-based failures. We're obviously seeing that electromigration limits are constantly decreasing with every ongoing technology, and 28 nanometer is no exception. Similarly, on the ESD front, we've seen that the ESD design windows have constantly decreased all the way from 90 nanometer to 40 nanometer. And going to 28 nanometer, we are seeing an even larger decrease in the actual design window. The ESD design window is essentially the window between the operation of the actual IC operating area and the IC breakdown area. GlobalFoundries and ANSYS Apache are basically partners to be able to provide the actual reference flow for doing advanced reliability simulations. ANSYS and Apache are essentially 28 nanometer design ready. What that means is we offer a complete technology file integration into your RedHawk and Totem platforms to support the GlobalFoundry PDK. And we obviously have silicon-proven accuracy and sign-off, meaning GlobalFoundries has obviously considered all the different rules that we offer and made sure that they are in line with the silicon sign-off conditions. We offer a complete digital reference flow for power sign-off, basically doing static and dynamic voltage drop analysis, power and signal EM analysis, being able to automatically identify design weaknesses and fix those design weaknesses within the platform. We are completely foundry qualified for both reliability as well as for IR drop analysis. Let's look at a sample digital reference flow from RedHawk. Typically, the RedHawk reference flow has several types of design inputs, several types of technology inputs. For the 28 nanometer, we will be using the GlobalFoundries 28 nanometer PDK. In terms of the design data, you will be feeding in the left def of your design or the GDS of your design. And finally, the library data is going to be coming in as a .lib or a GDS or a APL, which is an Apache Power library. The RedHawk platform can perform multiple types of power, noise, and reliability simulations, including power and ground connectivity checks, which is early analysis, static IR drop analysis, which is a DC simulation, advanced dynamic voltage drop, which is a transient picosecond by picosecond simulation of the complete transient behavior of the die, and finally performing power and signal electromigration analysis. In order to ensure that our 28 nanometer power grid has high integrity for both voltage drop as well as electromigration, we need to check several different aspects. In terms of low power design, our actual power transients are becoming more and more important, but not the actual power consumption. Power transients needs to be captured in terms of simultaneous switching aspects, in terms of in-rush current, and in terms of impact through the package and voltage regulator modules. In terms of electromigration, we need to make sure we identify the actual EM bottlenecks for different metal layers, all the way from the topmost metal stack to the actual device layers. We also need to make sure that we consider the entire timing impact of the different switching scenarios in the die, making sure that different cores turning on and turning off, different memories turning on and turning off is not causing simultaneous switching effects, which could cause device failures. Apache also offers an automated design prototyping and optimization platform. An automated design prototyping is essentially being able to automatically generate the power grid at an early design stage and prototype different types of power grid in order to ensure that you don't have any EM bottlenecks or IR drop bottlenecks. The optimization platform is what provides an automated mesh optimization algorithm to make sure we meet your design guidelines for IR drop. We also do advanced decap placement in order to ensure that the decaps are operating at the right frequency component and not providing enough current when needed. In the low power design space, we also offer automated switch placement and switch selection, where the user can prototype different types of switching behavior, as well as different types of switch placement, and prototype the different analysis scenarios to get your optimal power grid design. Let's go into the support for the 28 nanometer EM reliability rules. Typically, when it comes to EM, it has always been represented as a current limit in terms of milliamps per micron. But as we go towards lower technology nodes, we're seeing that different EM limits are coming into picture. We need to make sure that the EM limits are dependent on the width of the geometries. The EM limits are dependent on the length of the geometries, and sometimes even on the current direction. Being able to handle all these different types of EM rules is increasingly important, especially on the 28 nanometer PDKs. We also need to be temperature aware, topology aware for different vias, via array aware, and we need to be able to do simultaneous analysis both on a transient approach as well as on a DC approach in order to capture RMS, average, as well as peak reliability limits, or EM limits. Going a little into the ESD platform, Apache offers a comprehensive ESD analysis framework which can model the different pathways that are needed to shunt ESD currents. ESD is nothing but a transfer of charge from one body to another, which could basically have a catastrophic impact on your actual object. So in this case, an ESD victim is essentially a chip that is being discharged or charged because of a high charge event. In order to protect a device, we typically place clamp cells or diodes that can shunt the current away from actual operating devices in order to protect them. To be able to model these shunt devices and to be able to model the actual current flow paths is going to be very important when performing ESD simulations. ESD simulations can either be represented as resistance checks between different points in your power and ground network and signal network, or current density failures that could burn the actual current, or rather the actual wire, during an ESD event. Here's an example of a layout connectivity check where you have a pad and different power and ground networks. Typically between a pad and power and pad and ground, you will have ESD diode elements. And typically between a power and ground network, you will always have an ESD clamp element. It's important to be able to recognize these ESD devices and also be able to model the different parasitic pathways between the power and ground network and the signal and power and ground pads. It's also important to make sure that we do cross-domain checks. Typically in ESD analysis, we need to make sure that you have a cross-domain check between multiple power and ground networks. This is to ensure that these complex pathways do not get triggered during an ESD event. Typically, a back-to-back diode is placed between a power and ground network if they are in different domains. And the platform needs to be able to analyze this in order to show your ESD failures. Another important aspect of ESD is being able to understand what is the amount of current that flows in every via and every metal during the ESD event. As we are going towards lower technology nodes, especially 28 nanometer, the actual current density limits for an ESD event has significantly decreased. Because of this decrease in the current limit of your metal and the vias, we need to ensure we have a simulation-driven approach to capturing the current density behaviors. A simulation-driven current approach essentially checks the different current flow pathways and compares it with the actual peak EM limits in your design. The next is low power applications. GlobalFoundries and Apaches have partnered to ensure that low power design analysis is going to be a success in your first time tape out. This is essentially to make sure that you have different types of analysis availabilities from the Apache platforms, especially being able to handle power-gated designs, being able to handle inrush current analysis, and also advanced reliability modeling, especially using LDOs or on-die regulators. If you look at a simple power-gated design, you typically have either a header switch or a footer switch. It's important to it's important to model the behavior of these switches to understand the impact of voltage drop across the different switch nodes. It's also important to model on-die regulators, especially regulators that can respond faster than off-chip regulators, and also regulators that can directly affect the voltage drop at the output of your different power and ground networks. Power-gated memories are also becoming extremely important in low-power designs. Every memory can go into different states: a sleep state, a deep sleep state, a power-gated state, an off state. It's also important to be able to analyze these different states using a platform, especially the Totem or RedHawk platform, that can give you complete picture of the inrush current as well as the reliability during the inrush current. Being able to understand wake-up times or sleep times of either the entire chip or the core or independent memories is going to be important in designing your low-power chips. At the SoC level, it is once again important to analyze the impact of simultaneous charging and discharging of controlled power and ground networks. In this case, I'm showing an inrush current example where multiple switch or multiple power gates are being turned on at the same time. Obviously, if you turn on multiple power gates at the same time, you have a higher inrush current. And if you turn on only a few of them, you have a lower inrush current. So there is a trade-off in terms of turning on a number of power gates in your design and the time to actual wake up in your design. The RedHawk low-power platform can perform these simulations, including the complete impact of the package, the power delivery network on the die, and the switch transistors, along with accurate switching transitions between the transistors for a complete low-power analysis. RedHawk can also prototype different types of power gate placement or switch placement and analyze the design with these different switch placement scenarios. Going to the complete digital reference flow, as a customer of both Apache and GlobalFoundries, you will have access to the complete technology and library data, the standard cell left-F, and the characterization. You will be performing the actual characterization by yourself. And going to the actual analysis platforms where static, dynamic, voltage drops, low power analysis will be performed with the help of Apache tools. And finally, your design, hotspot fixing, and analysis and root cause identification will also be performed in the analysis platforms. Essentially, RedHawk and Totem are Apache's platforms for performing power, noise, and reliability at your SoC and your IP levels. To summarize, GlobalFoundries and Apache have a tight collaboration to make sure that 28 nanometer reliability and analysis is a success. We also support the complete 28 nanometer standard cell libraries and also enabling the complete power integrity and reliability of your complete IC sign-off. A download toolkit is available for the 28 nanometer reference flow from GlobalFoundries. Now we will break for questions. Thank you.